Okay, I'm starting the recording right now, and I'm gonna uh, flip to my lectures here. Did I share my lecture? See, yeah, here is my lecture, and let's have this one here in the presentation mode. All right, so this is our regression lecture, and as I stated earlier, this is our first supervised learning, okay? And let's go through a few definitions and exercises as always we have been doing. So in this lecture, before we get into the terms, the technical terms, let's assume we have a collected data about students, okay? See if I can get my pen here. And basically, I collected how many points? 1, 2, 3, 4, 5, 6, 7 points about students. And I asked these students about how many hours they study, right? And what are the what is the grade they have achieved? Okay, all right. So this student, for example, studied, let's say, I don't know, zero point 0.9 hours, and they achieved, uh, let's say, a 1 point something grade. This student studied for 1 hour and achieved a grade of 4. Okay, so obviously what I have here, we are having some kind of dependent variable, which varies based on independent variable. I can think of this grade as y and this one as x. Okay, and now what I want to develop is I would like to develop a model that can predict the grade of any student or studied any hours. Let's say, for example, if I want to predict what would be the grade of a student who studies 2.5 hours. Okay, so this is solved by one of the supervised learning, which is called a regression. Now, in supervised learning, we have regression and classification. And let's see what's the difference, supervised learning, between regression, right, and classification. In regression, the output is continuous. I can have an output for these grades from 0 all the way to 14, 100, whatever. And my output can be, let's say, 1.95, for instance. So the output here is continuous, right? In classification, the output is discrete. For example, I need to classify this image either to be a dog or a car or a tree, right? Or a house. So I look at image and then I need to classify it into these 4 categories. In both cases, regression or classes, I'd have to develop a model which is being trained on this data, right? And sometimes the training process, such as in the case of regression, produces continuous output. Sometimes the training produces, or the output produces discrete output. So both of them, we refer to them as supervised learning because we give data with labels. In this case, I'm giving you what a student that studied 1 hour, what is the grade? That's the labeling. I'm giving you the input and the expected output. Versus unsupervised learning, you don't have these labeling. You don't have expected output. You have to dig into the data and do the clustering and dimensionality reduction without data being labeled. Okay, you don't have here the concept of you produce an output and compare it to expected output. There is no expected output that I can measure against in unsupervised learning. But in the supervised learning, I have an output that I can measure. Here are my training data. This is the training data. This is training data. This training data. This training data. Training data. So this is the class of data that we are, or algorithms that we are dealing with. Now, in terms of regression, as we said, our output is continuous. And to answer this question, which is to develop a model for me that predicts the grade for any hours, we will do regression analysis or line fitting. Okay, so now to predict a grade for a student who has studied for 2.5 hours, we perform regression analysis or line fitting. Okay, and then we can predict the grade of the student. So now notice this is the line fitting that I did. Okay, this is the line fitting. I have to perform line fitting either graphically, which obviously not practical, or analytically. Okay, or later on we'll see there are dedicated machines for that, like the neural network. Okay, so but in this class, in this lecture here, we'll do simple stuff. Okay, we'll do the linear regression, as we will see. So once we develop the model, which is this line, the black line, I can say, all right, well, for 2.5 hours, what would be the expected grade? Oh, 6.3. Good. Right? My model now predicts a grade of 6.3 for a student who studies 2.5 hours. So the question is, how can I get this model? Okay, now, so regression analysis, okay, is estimating the relation between dependent variable. Oh, okay. In this case, will be the y, the grade, on one or more independent variables. In my case, it's the x or the study hours. Okay, so dependent variables can be called in other textbooks or literature as output, outcome, response. The independent variable can be called predictors, covariates, features, explanatory variables. Okay, you can see all these terms. Okay, two main types of regressions: linear and nonlinear. Okay, and in this lecture we're going to do the linear regression, and later on we're going to touch upon the nonlinear when we go to a neural network. What do you mean by nonlinear? Well, let's say for example here, okay, the example of grade versus study hours. Okay, let's say, for example, I have the students. I sampled the students, and I ended up one student here, 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 one student here. Okay, basically, this model says the grade improves up to a point. Then if you study more, then your performance degrades. ممكن انك بتصير تعبان، بيزيد ارقك، بيصير عندك ستريس، وهذا بينعكس سلبي على علامتك في الامتحان. This is an example. Now, such a model, there is no way I can predict this in a linear model. يعني, how do I, what kind of linear model? I can't fit it. I cannot say this or this or this. There is no, so this is non-linear هلا. Okay, and you really need to go to nonlinear solutions. One of them is the neural network, and it does a superb job for that. Okay, once we get to linear. So this lecture is for linear regression models. So here is an example, okay, of my data. The one variable, right, independent variable, and the dependent variable is y. So the question is really in our analysis here, in our linear regression, becomes how to find A and how to find B. Now I'm assuming that we have one variable because in linear variables, I can have more than one variable. Okay, I can have, as we'll see shortly. So it becomes a question of how can I find these two, A and B? Find out those. Once you find them, خلاص, you finished your model prediction or line fitting. Okay, so now I think might have skipped one. Let me see if I have. Okay, well, that's fine. Okay, right. So our focus, we said in our linear. Now, uh, how can I fit a line that really is best for the data? Well, I need to find a method to a criteria method to designate that this is the best line. So one method is to select a line with the least squared errors. All right. Okay, so this is measuring criteria. So because you have to tell me what's my success criteria, what is the criteria that I need to look for so that I can differentiate between this line and this line? Because I can have students that perform a project on this data, right? And I have a student that has this dark black line, and then I have another student that has another line. So which one is better? So one criteria we can use is the least square errors. And the least square errors says what? We sum, so you can see this data is, let's choose, first of all, let's erase what I just draw here. Okay, that's one thing. Second, let's choose a pen with a distinct color. Probably here we'll choose the green. Okay. All right. So now this is my line. Okay, and this is the data. So then what do I do? Notice that the line, it's impossible that the line has to go through all the points. So there are these distances between the points and the line. Okay, I call these errors or residue. Error or residue. So I measure these distances, square them, sum it to the square of this error, sum it to the square of error, sum it, sum it, and then I create the squared error, the total square error. And the best line is the line which has the least squared errors, the least squared errors, which says in another way, it is the line that is really as close as possible to all the points, right? This speaks another way of seeing it. Of course, how to evaluate mathematically. Well, we bring this. This is the A and the B that we estimated for our model. We evaluate every point. Okay, so to get let's say for example here, we evaluate the point. This becomes my point according to my model. Okay, and we subtracted from the y from this model. The model say the data says you should be here. So this is now my error. I square it and I add it to the other errors. Notice that this point here is what the model predicts. This point here is what the data is telling me. The difference between them is the error. طيب سؤال, why square? قصتها طويلة هذه, بس احنا because we would like to have positive quantity. Why not take the absolute value? مشكلة الابسولوت value بتغلبني في derivatives, right? Because now we need to derive these equations. فsquaring حلو nice وبيعطيني easy derivative without a problem. The absolute value for derivative is you have to know if this is positive quantity, negative quantity, ولا قاعد بالterms. Okay, but so that's why with the square we square them because it simplifies the further steps that I have to go through. So the sum of squared errors is my criteria here to choose the best line. Okay, and I would like to have the least squares, right? So now, if you see, if you keep changing, the slopes and the lines, you can see that the lines every fit you do has a sum of squares, sum of squares, sum of squares, and your best fit is the one that gives you the least square errors. Okay, so you can when you vary A and B. All right. Now, one quality of line regression is referred to as the R square measurement. And the R square really measures how well your linear regression is. It really indicates the variation of the dependent variable, in my case, the Y, or the grade of the student, that is predictable by the independent variable, X, or in my example, the study hours. So the more I can predict the behavior, the better it is, right? Let's say, for example, if I can predict the attendance of the students in the Hashemite University by the temperature, right? So if I do my analysis and say, well, the R square tells me that this temperature is very strong indication of how much how many of the students, I'm sorry, how many of the students attend the school, then this is a very good linear model because you are capturing the variability, which is the attendance of the students, the dependent variable, by your independent variable, which is the temperature. That's what you want, basically, right? And the R square can vary from 1 to 0. 1 means that a model explains the variability in a very well way. The 0, it means it cannot explain it. So you really, from 0 to 1, you want to be as close to 1 as you can, right? 0.8, 0.9. Although really in some fields of science, it's very hard to get even above zero point 0.5, especially when you study human subjects. So a 0.3, 0.4, it will be a great win. Okay. All right. So you have to check with your domain of study to understand the appropriate R square value. But in general, you want to be as close as possible to 1. Okay. So how do we calculate R square? See if I, okay. All right. All right. So calculating R square, really, we need to compute something called the sum of squares around the mean. Okay. So basically, all right, we need to find out the mean of the data, okay, and subtract it from the data and square those. And this is the data. So for example, if I have here my y-axis, okay, so this is uh, this is my y here, and this is my, yeah, the x. All right. So if I have my points here and here and here, so what this one says, let me. So I'm gonna have to reflect those on the y-axis. These are. So let's say, for example, this is where my average is. So it says I want to subtract these points from the average, okay, and square them. In other words, we have seen this before in our PCA analysis. You want to bring all these points that the data point as to the origin point, right? And create for them new coordinates, which is yi minus the average, right? So basically, when you subtract the average, you are really moving the data to the origin, as we have seen in PCA, and then square them. The sum of their squares, okay, which is yi minus the center, is called the SS mean, which is the sum of square around the mean, the sum of square around the mean. Now, if you do the same exercise for the fit, right? This is when you subtract the data, the y's, minus the line, what the line predicts. Now, so suppose this is my model here, right? This is my model. Basically, I found out what's A, what's B. Now, when I subtract the points, the data from what is being predicted, the data from the predicted line, and square them, I get what is referred to as SS fit, right? And now if I divide both quantities, the S by the N, I get the variance. all right? The variance of the fit and the variance of the mean, okay? Now, R square is computed by, let's see, these are the simplified expression, 1 minus, I prefer this expression, and all of them, they are the same, 1 minus SS fit over SS mean. Notice that when this approaches 1, right, it means SS fit over SS mean is as close to 0 as possible, which means that your really your errors here are very small, right? These errors here are small compared to the mean. But when these are huge, right, around the mean, then this quantity now approaches the 0. Okay, all right. So that's basically what it means. Okay, so R square is a metric which is used to measure the efficiency of my model. Okay, now here is an example, a numerical example, and we will go over this numerical example to explore how we can build a linear model. So let's say, for example, I have this data. I have this is my dependent variable. This is my independent variable. And these are my 3 points. And my question to you is, notice the 3 points are simple number of points. In reality, no one is going to ask you to build a linear model with 3 points. We do smaller examples so that we illustrate the idea. When you have hundreds or thousands of data points, this is when you have to use software tools and you program your solutions in these software tools or software languages. In these 3 points, we would like to develop a linear model, something like this, okay, which minimizes the sum of square errors, okay? We know now what's the squared error, so we want to minimize the sum of the square error. Okay, so that's the goal here. So how we can do that? Well, first of all, let's find out what is the sum of square errors. زي ما اتفقنا, you take every point predicted by the linear model, subtract it from its data, right? Add how many points I have? 3 points. So this will be like 3 points. This becomes your total squared error, or what it is referred to as the loss function. Okay, so the loss function here, what do I need to do? Well, I need to find the optimum. Okay, so you can see this loss function. You know, if you study this very carefully, you will see this the loss function vary with a, right? Something like this. Okay, so we want to find the least loss function. Similarly, it varies with b, right? This is b. This is the loss. We want to find out this bottom point. And how do you find out the bottom point? Well, you derive the loss function with respect to a and you equate it to 0 to find out this point. Okay, and that gives you the optimum value of a. And you derive this one with respect to b and set it to 0 to find out this point and the corresponding value of b. Now, so the very first thing I have to do is to construct the loss function. Now here are my data numbers. Okay, so let's see if I can get. Here are my data points. So here's my x1, y1, x2, y2, x3, y3. All right. Now let's get the loss function. The loss function. Now I'm assuming my linear model is ax plus b. I'm gonna solve for a and b here. So notice that here, right, that my data point is 4 because this is 4, right? And what is this here? Well, I'm assuming that if I plug in this number here in my linear model, so x is 1, so a times 1 plus b. So this is a times 1 plus b. This is what my linear model will evaluate point x equals 1. Square the quantity because I want the square error. Do the same thing for the second point and the third point. Add all these errors. That gives you L. Now, if I derive L with respect to A, I have to go through some derivation work here. This is just your basic math. And I get this equation here. And from previous slide, what we said, we derive and then we set to 0. Okay, so I set this derivative, which is delta L over delta A to 0. I do the same thing. I derive this equation with respect to B and set this equation to 0. Now I have two linear equations, right, with two variables. What are my variables? A and B. And I solve for A and B. If I solve these equations, I'll get A equal 2 and B equal 4 over 3. So these are the values, right? Now this becomes my linear model. This is A, and this is B, right? This is my linear model, which does what? Which minimizes my loss function, which is the sum of the square of the error. Now, warning, there's a little bit of math here, Jamaat al-Khair, okay? So, so please do this exercise, spend some time, convince yourself that this is the correct sum, and this is the correct derivatives for A and B. For those of you who don't know how to derive L with respect to A, please review your calculus or differential equation courses so that you are following up with us what we are doing. Okay, so now this becomes my linear model, and I can plot it here. Okay, then I can tell you that this is not the only way of doing it. There is a general formula for that. وبتريحني من derivation, computation of L, and the general formula says we need to compute these terms, okay, and this is called the sum of crust variations between x and y, and the sum of squared variation. Okay, and so the cross variation is when you multiply these centered points, okay, and xi minus average, you are centering the x data, and y minus, you are centering the data. So the distance you move to center the data, you multiply those for x and y. There is an easier form for that, which is multiply x and y for every point, and you subtract it by n times the average of x and y. So these are the averages of the x and y. And we need to compute as well the squared variation of x. Instead of x and y, we do x twice here, okay? And again, this is the simplified formula. If we do those, then A becomes SS of XY over SS XX, and then the B is evaluated as such. So let's go to our example. If we go to our example, right, and you notice that these are our points, okay, the same example, and this is the average of the x coordinate, the average of the y coordinate, then I can compute the SSXY and SSXX, and this is 16 and 18. A equals SSXY over SSXX, and get a 2, which is exactly the same value we got when we derived. And the B equals y average minus A x y, and this is the A coming from here, and this is the y coming from here, and this is the x is coming from the average x here. You do the math, you get 1 and a third, which is exactly what we got from our derivation model. So this is a general formula of building your linear model, okay, instead of going through the derivation. Okay, so now let's compute the r squared for our example, and in this case we will use this this one here, 1 minus whatever formula actually you use. So SS mean, okay, y I minus average y, square it, and these are the numbers. Okay, please look up these numbers and convince yourself that this is the data point minus the average, the data point minus the average, data point minus the average, and this is what you get. And the SS for the fit, okay, the data point, and this is the value for the line for predicting the first data, the data, the value of the line for predicting the second data, etc., and you get this value. And now computing R square, it will give you 0.9231, which is very close to 1, which tells me that this model is really a good model. And you can see it actually graphically. You can see this model is close to the point. Okay, it minimizes the errors perfectly. Okay. So it is a very good predictor. So if I tell you that what's the value, expected value when I have x equal 2, so okay, well, it's probably a 5.4 or whatever. So this is really good from this value. Okay, multiple linear regression models. So far we have what? We have ax plus b. I have one variable here. Can I have multiple variables? And the answer is yes. We can have multiple variables. And here's the answer, right? You can have multiple variables. You can have, this is your intercept, which mimics b here, and these are your variables x1 and x2, and these are the slopes for every variable. Okay. All right. In fact, you can have multiple independent variables. Okay, not just one y. You have multiple y's. So in this case, I have multiple independent variables and multiple dependent variables. These are independent variables, and these are the y's are independent variables. Okay, so so you can have here is an example of a multiple variable, but one dependent variable and multiple independent variables. So what we want here, we want to develop a regression model to predict the exam score y, okay, based on three variables: study hours, number of practice tests, and sleep hours. And so we have this data here. So this is we sampled how many students? We sampled 4 students, right? These are the students that we sampled, right? And these students, and the first student, when this student studies 5 hours and practices 2 tests and sleeps for 7 hours, it turned out that this student score was 75. The second student slept for 8 hours, took 3 tests, preparation tests, and the student slept for 6 hours. His grade or her grade was 85 points. Third student studied for 6 hours, took 1 practice exam, okay, and slept for 8 hours, and the grade was 70 out of 100. And the last student, studied for 9 hours, okay, and took 4 tests and slept for 5 hours, and his grade was 90. Okay, so now we need to solve this. And obviously, we went in and did our numerical analysis, and we came up with 2 models. One model said, well, the solution, okay, and obviously we need to solve this equation. This is one solution, possible solution says 50 plus 4x1 plus 5x2 minus 2x3, right? And obviously these pluses and minuses are corresponds to this B0, B1, and B2, and B3. All right. So you can see that this model rewards that the variable x1 and x2, and these are what? The study hours and the number of practice tests, but punishes x3, which is what? The sleep. So the more you sleep, the less the grade you have. This is the model. Another solution that we worked out during numerical methods is this solution here. So if we plug in the data, and let's see how these models compare. So we said, okay, let's try to evaluate y1, Okay, and let's try to evaluate y2. And notice that here is y or y hat and y double hat, or y prime, y double prime. So y for the first student, y prime predicted 66, and second model predicted 75. Obviously, this model wins, right? For the second student, the first model predicted 85 versus 83. So obviously the first model wins. The third student, the first model predicted 63 versus 17. Obviously this model wins. And the fourth student, the first model predicted 96 versus 90.7. So obviously, the second model wins. So clearly, from this very quick analysis, the second model really wins. But if we want to be really more accurate, we have to calculate the R square for the two models. And maybe the R square for this model, maybe, for example, I did not compute it, is 0.6, and here it's 0.7, and that's why you are getting closer results to the predicted model. So this is an example of what? Of a multiple variable linear regression model. And clearly they are very, very useful for these cases. Now, last point here is that when we talk about data, and this is, by the way, covered in data science, and you get all these points, since I'm getting points and I need to train them for regression or for classification. One key point is to detect if a data is an outlier data. So let's say, for example, you have this data here, and of course, these data are clustered nice and clean, and also you get this thing popping up there. So obviously this data, it looks suspicious and possibly erroneous data, and the sources of error could be data entry, human error, or sampling error. You have a sensor ضرب معاك في الفيلد، بدل ما يقرأ الحرارة صح بيقرأ لك درجة حرارة بطريقة خاطئة جدا, or natural variation due to abnormal conditions. And so in all cases you have an odd data. What do you do with it? Typically what we do in to detect outliers is that we have to compute the z-score. This is very similar to what we did in the standardization step in PCA. We remove the mean from the data, and we divide the data by the standard deviation, and that is what is referred to as the z-score. Now, if you look at the normal distribution of data, and you see that the distance from the mean from this side or from this side of a sigma here, or one standard deviation, this typically were 68% of the data. If you increase the distance all the way to two sigmas or two standard deviation, then you are covering 95% of the data. Now, when you go beyond that all the way to plus or minus 3 standard deviation, you cover 97%. So typically, when you are really above, let's say, for example, away from the mean by 3 sigma or 3 standard deviation, then one would say, wait a second, is this normal data? Or there is something, so this is basically this here. This is away from the mean. This is probably 3.5 sigma or more. Okay. Well, what's up with this data? Is it error? Is it sensor gone wrong? What it is? So really, you want to kind of deal with these data, because these offshoot data will down in the line mess up your analysis. Now, if they are normal data, and you are sure they are correct, and you want to include them in your analysis, that's fine. Then this is our this is what we want. But more likely than not, these type of situation leads to to data that erroneous, or there is some kind of problem during sampling. So we have to replace it by either discard it or assume an average value. So there are ways to deal with these kind of offshoot data samples, as you will cover in your data science course. Um, the reason I brought this because this lecture is the lecture where we started our supervised model training, where we take the data and build models on it. If your data that you take is not correct, then, as they say, garbage in, garbage out. You have data which is inaccurate, incorrect, you will get a model which is inaccurate and incorrect. So it starts with data. And that's why we popped up this little detour here towards computing z-score to tell you, make sure your data is correct. Make sure your data will result in meaningful algorithm results. Because we'll take the data and send it to a neural network, we'll send it to reinforcement algorithm, and whatever, if things are inaccurate, you will get an inaccurate results. Okay, with that, I think I finished my presentation for the day. To sum up, we have explained in this lecture linear regression, which is part of regression, which can include linear and non-linear. And the regression is part of the supervised learning. In fact, this is the very first lecture in supervised learning. We said that in supervised learning, we have training data, all right, which is the points that we have seen in our the data points that we have seen, whether in the example of the three variables or the one variable. And we took this training data and we built our model so that we can predict any other value for the independent variable. We covered the R square as a measure of how good the model is. We say the R square varies from 0 all the way to 1. You want to be as close to 1 as possible, because that means that your independent variable explains the variations in the variation in the independent variable variation in the dependent variable. And that's what you want. Okay, with that, I conclude my lecture, and I'm going to turn off this presentation and leave my, if I get my here, go back to my recording and turn off the recording here. Recording. Okay, stop the recording.